talk about decision tree. So it's a machine learning algorithm which can be used for both classification and regression. So it uses a series of simple logical decisions like if or else statements, structured like a flowchart or upside down tree like that tree data structure to arrive at a final prediction. So a decision tree mimics how humans think and make decisions. So humans' way of thinking is like the if or else statements. So if this, then that. So like that. So that if else is represented like the data structure. So the decision tree algorithm. So let's take an example of a data where we have to predict the output variable if we go for work or not. If we go for work or not. And the features we have is the weather, if it's sunny or rainy. Similarly, let's say we have another feature telling about the day of the week. So if it's a weekday or weekend, weekday or weekend. So by observing, let's say the data naturally have the type of data where the output is the person goes for work if the day is sunny and it's a weekday because that's obvious. So here you can see that mimicking how the humans think. Like if we don't go for work, the weather is rainy and the day is the weekend. So that's how the data will be present at the data set. Let's assume. So logically we can build a if else tree. Like tree means like set of decisions. So first let's say if the day, so because this is the most important logical, let's say if we asked if the present day is the weekday or weekend. So it's a weekday, then we ask another question if we about the weather, like if it's sunny or rainy. So if it's sunny, then we would probably go for work, and if it's rainy, we probably wouldn't go for work. Similarly, here, if it's a weekend, we won't go for work. So here, we, we can see that we logically build a simple decision tree based on the data which we have, and on the each nodes of the tree we ask a question about a feature like if the weather is sunny or rainy, or here we ask about the day if it's a weekday or weekend, and finally we achieve the output. So what basically happens while training decision tree is here on the starting node, which is called the root node. Here we have the set of all data which we have, and initially we ask the question about which feature we need to split on, so that we will discuss later. So here we chose the feature day and we decided to split the data, so we will split the whole data. Let me write it here. So we split the whole data into some partitions, and here while splitting the data in the output variable, which is the work yes or no, we will split it in such a way, we'll choose such a feature such that we get homogeneous output. Homogeneous output. So what do you mean by homogeneous output? So after splitting, let's say here we have a set of data in the output variable or output data here. This is yes or no. There are, let's say, 5 data which says yes, and we have 0 data which says no. So here it's homogeneous because we have only uh, we have 0 data which is belonging to the no class, and we have 5 data which is belonging to the S class, because here there is nothing in the no class, so it's homogeneous. Similarly, if it's not, then we would have something like 5 and let's say 3. So this is not homogeneous. So our end goal is to split, if in every step we need to split such a way that we have homogeneous set. So that's when we can make confident decision about about splitting. So here, if let's say a split gave to this set of data, we can confidently say that while doing the split decision, while doing the split and making the decision, we can say that this belongs to S class, which is the person will go for work definitely. It's not possible here because we have the both chances of becoming yes and no. At this, we can confidently say that the person will go forward depending on the previous feature split. So similarly, in each step, we need to achieve this homogeneity in the split. So here we will have some homogeneity. So at the end, in the leaf nodes, we will have the perfect homogeneous split. So it might not be always like 0 or 5 on uh, like the perfect zero, perfect split, because of the real life data where we cannot achieve the perfect split. But we need to try to split in an optimal way such that it reaches close to the homogeneous split. So what's a decision tree? So we build this tree via a series of if else question based on the feature which we select using different methods which we discuss later. So using those feature, we need to do the split such that we get the homogeneous data split in the end. So it can make informed, well optimized decision by the split. So let's talk about Gini, impurity, and entropy. So these and some other are just the metrics which are used to measure the homogeneity during a split of data. So using only this, we can decide which feature should be split on based on the lowest measure of the homogeneity or whatever, so that we will get more homogeneous split up. So in this example, we'll talk only about impurity and we'll use them in our problem, but either way, I'll just explain the intuition behind both. So the Gini impurity formula is, so this one is 1 minus probability square summation added over each classes. So, so this is the measure of impurity. So if you have more impurity, they will be less homogeneous. So our goal is to reduce the impurity. So you have to choose such a split. So where do we get this formula from? Why do we take the probability square instead of just the probability itself? So for that, let's take an example. Let's say we have a bucket where we have some coins which are facing upwards. Let's say we have 10 coins and 7 of which are facing heads upwards and 3 of which are facing tails upwards. So we have those probability represented here. So let's say we are picking a coin from it and we are making a prediction or guess, and you know this probability already. So no matter what you pick or what the outcome is, you will always guess that it's heads 70% of the time, and you will guess that it's tails 30% of the time. So it is the probability itself 0.7 and 0.3. So these two are independent events. The probability, which is we know already, which is already present in the coin, so that one, and the probability which we predict, and the actual probability which is present, or let's say this is the actual data. So these are independent events. So the total probability is just we can multiply this both. So that's where uh, the square thingy comes from. So let's say what's the probability that you correctly predict that it's a head, which is 0.7 times 0.7. Similarly, what's the probability that you will correctly predict that it's tails, which is 0.3 times 0.3. So this is the probability of the data which is present. Also, the data which you predict, both are same, and which is correct prediction. So this can be interpreted in that way, and that's why we multiply them. So it would be 0.49 and 0.09. So if we add them together, which is probability of getting the whole prediction correct. So this is the correct prediction for head. This is the correct prediction for tail. So we add them both, which is nothing but the summation of probability of heads squared and some probability of tails square. So if we just add this, we can just represent it with the summation. That's where the summation symbol comes from. So which is we calculated already. If we add this both, we'll get 0.58. So this is the probability of the whole thing or prediction being correct. So now we need to measure the impurity, which is the probability of misclassification, so that we can reduce it and achieve the homogeneous split. So in order to measure the impurity misclassification, probability of misclassification, that is, we predicted wrongly, which is nothing but 1 minus this thing, 0.58, which is we will get the value of the misclassification, which is 0.42. So this is what the Gini value is, which is nothing but the impurity or misclassification. To put in short, why do we take square? Because it's the predicted and the actual data, so that we multiply them because of the independent events, and we add them together to get the total probability of correctly predicting across every class. And we take the subtraction of 1 minus the same thing which we calculated to measure the impurity or misclassification here. So if the misclassification here, which we predicted here, if the Gini index is 0, which implies that this term would be 1, right? So 1 minus 1 is 0. So in that case, we can say that our guess is completely correct, and we would have 1 on this side, as we saw before. So which means we guess everything correct, so there is no impurity. So that's why the Gini index would be 0. In other case, let's say we have 5 heads and 5 tails. Would have a correct guess probability if we have 5 heads and 5 tails. Correct guess probability would be 0.5 square plus 0.5 square. So because we have an equal chance, so that the total would be 0.5. So this is the probability of guessing it correctly or predicting it correctly. So the Gini would be 1 minus 0.5, which is 0.5 itself. So this is the highest possible value for a binary classification. Now let's talk the intuition behind entropy, which is also the measure of homogeneity. So here entropy, which is nothing but it's a measure of uncertainty or disorder in a probability distribution. So what uncertainty or what's disorder? Let's see. So first, let's see the entropy formula, which is given here. So it's minus summation for all classes. We just multiply the probability and the log base 2 of the probability. Let's break on this formula. So let's see why we take this log value here, log base 2. So we have log base 2 of the probability. This concept actually comes from information theory. So when we take log of the base 2 of the probability, we get something which is called as information. So information which is measured in terms of bits, just the computer bits, the 0 or 1. It's measured in form of bits. Bits is nothing but the information which we get after making a decision. So in other words, we can say how many number of questions we need to ask to make a decision. So what do we mean by that? So let's see an example. So let's take just a simple coin toss. So we flip the coin, we get head or tail. So initially we know that it can be head or tails. So here we need to ask only one question. So is it head or tail? So that's what information here is. So which is measured in bits here. It is 1 bit because the information which we need here is more because we need to ask one question. So if we were just certain if the coin is like 100% biased, if only giving hits, then we need no information. So the bits will be 0. So the more the information, we will have more surprise because we will be less certain about what the outcome would be. So if the bits is less like 0, we will be more certain. So we would be less surprised. That's the concept of the bits and measurement and information, measurement of information. So let's say instead of the coin, we have another set of outcomes. A, B, C, and D each have the probability of 0.25 in being chosen. So here, let's see how many questions we need to ask. How many binary questions? So here we need to ask if it belongs to A, B, or C, D. So these are binary question, yes or no. So similarly, again we ask if it belongs to A or if it belongs to B. Here again we ask if it belongs to C or it belongs to D. So the outcome is belong to what class? What of these 4 classes? So here if you see we ask 2 questions. So one question is here we ask if it's belonging to this set or this set. Another set of question is asking if it belongs to the individual element in this set. So we ask 2 questions. So the information which is needed here to classify them is or to separate them is 2. So it's 2 bits or 2 set of questions. Similarly on the coin it is 1. So this formula here from the information theory helps us to measure that. That's why we take log. How? Let's say the probability value is 1. So if you have the probability 1, log base 2 of 1 is 0. You'll get 0. So 0 means what? 0 is the information which we needed or the which is measured in bits. So 0 bits. 0 bits means no info because the event is certain. We know what the outcome is. So that's why we don't need any information in predicting that. It's certain. So similarly, let's see if the probability value is so the probability value is 0.5. What will we get? We will get the value as 1 minus 1 actually. Log base to 0.5 is minus 1. But entropy is always positive, measured in positive terms. That's why even you take the log values of these decimal values, the log base of decimal value is negative. So that's why in order to match that, we need to use the minus in the formula so that it can be positive. That's why we had the minus here in the formula. That's where the minus comes from. So in turn, this would be positive. The formula it will be negative, so it will be positive 1. So what is positive 1? Positive 1 represents that we need one information or one bit of information, one question we need to ask. So that is when the probability is 0.5. So the case which we saw before, tossing a coin, it has the probability of 0.5 each, right? So, and we need to ask just one question. So this is given by this formula and this example here. Similarly, let's say if the probability value is 0.2. So it is the case when we saw there is 4 events, each ABCD, and each has 0.25 chance of occurring. In that case, minus of log base 2 0.25 is 2, which represent 2 bits of information. So if we recall, we remember that we need to ask 2 set of questions in order to separate these 4 events. So that is what meant by this measure of bits, which is a measure of information in information theory. So that's why we use the log base 2, and this negative value is to match the log. And now that we know the formula of the information, here the previous example which we saw, where the every probability is 0.25, which is not the case everywhere. Different classes have different probability. So this have let's say 0.3 or something. So we need to take the weighted average. Weighted average. So that just because they are different, we need to multiply this everything with the corresponding information which we calculated. That's why we and add them together. Add them together. We need to multiply with the corresponding probability and add them together. That's why we have this multiplication of the probability here, and we have the summation here. So that's how the whole entropy formula comes from here. So after calculating the entropy, the next thing we need to calculate is the information gain. Information gain is nothing but the entropy of the parent minus entropy of the child. So while splitting, we'll have in the tree, we'll have the parent and child nodes, right? While splitting. So we'll just calculate the entropy. What is entropy? Which is the measure of uncertainty. So the parent would have more uncertainty. That is, we need more information, to separate them. That is, they have less homogeneity. And in the child, we have, let's suppose we have the less uncertainty. So if we subtract those both, we'll also get a measure of uncertainty. So if we do different splits and calculate information gain, we should maximize this information gain so that this is what information gain is what helps us to reduce the uncertainty. So this says how much uncertainty was removed after a split. So after a split, the information gain, if it's more, means it says that more uncertainty is removed. So in turn, they will be more homogeneous, and that would be a most valid. Now let's see a numerical example to calculate and design the decision tree. So let's say we have this data here. We have the features, weather, temperature, and if it's windy or not. Output variable here is play, which represents if the place can be playable for any sport, which is yes or no. So first step is we need to calculate the Gini impurity or entropy and information gain. We won't be calculating entropy, we'll be calculating the Gini impurity here. The first step is we need to get the baseline impurity so that we can compare with the different feature for splitting. So to calculate the Gini of the root node, which is the first node, we will go ahead and apply this formula. So we have 3 nodes and 2 yeses. So we'll calculate the probabilities of them and we will just square them and take the summation as in the formula. So we have this and if we subtract 1 from it, you'll get the rho Gini as 0.48. So now that we calculated the baseline Gini to compare, so let's calculate the split, which is Gini impurity for each feature. The first one which you're gonna take is the weather. So for weather we have 3 classes: sunny, outcast, and rainy. So for each of them you're gonna calculate the Gini impurity. For sunny we have no just 2 no's and no s's. So we have the class count, so we can calculate the Gini for sunny. Similarly, we can calculate for overcast and rainy. Then we can calculate the weighted average of the Gini impurity for the weather. That is, we need to multiply this with the probabilities. So here the probability is 2 by 5. Probability of choosing sunny is 2 by 5. Similarly, overcast is 1 and rainy is 2. Multiply with the of the individual ones and add them together. We get the Gini of the Gini impurity of the whole feature if we split according to the feature. So similarly, we do for the next feature, which is windy yes or no. We similarly calculate the Gini impurity for each of these classes yes or no, and we calculate the weighted average so that we get the Gini impurity for the whole windy feature, which is 0.267. Now let's split the values with respect to temperature column. So here the values are continuous, while previously we saw only categorical separation. So if the values are continuous, what you have to do is first we need to write them in ascending order, the temperatures, and you have to find the mean or average between the consecutive values. So the middle value between 22, 20 and 22 is 21. And similarly for these two, it's 23.5 and so on. So we'll have 4 values. So now we have to calculate the Gini index, which is the weighted Gini for each pivot. So pivot means like first pivot we have it like here. So for one class we consider it as, for one split we consider it as the values which is 21 and less than 21, and the next part we consider it as the values which are greater than 21. So what do I mean by it? So here one split is 21 or less than 21, so which is only 20. So what do we have in 20? 20 is no, so we'll be having only no, so the Gini is 0. Similarly for the right part we'll have all the values, so we will have 22, this one 22, 25, 28 and 30 will have all these values, so these will be here. Similarly we'll calculate the Gini, and using these two we'll calculate the weighted Gini by just multiplying the probability values or the Gini values which is present on them. So similarly we're gonna move the pivot to the next one. So here the part 1 is 23.5 along with these values which are previous to it, and the next part are the values which are after it. So here we have the values which are equal to and less than 23.5. So what do we have here? We have 20 and 22. These are equal to or less than 23.5. So 20 and 22 is yes and no. So we have yes and no. So similarly, we will calculate for the right part and we will calculate the weighted Gini. So similarly, we will move the pivot and calculate for every uh, partition which we do, and we will take the least amount of weighted Gini. So now that we calculate the value of the Gini impurity for each of the features, we can see that the weather has the lowest Gini impurity, which is 0.2. So next thing we need to calculate is the Gini gain. So Gini gain is nothing but reduction in the Gini impurity. Reduction in the Gini impurity. So original Gini which we saw before calculating for any features is 0.48. We need to subtract this with every of this calculated Gini impurity, and we need to see which one has the most highest value, and temperature to have some value. So weather has the highest value, which signifies more Gini impurity has been reduced. So we need to choose the weather as the feature and do the split. So let's draw the tree here. So we will be having all the he will be having the root node. He will be having all the data, and we would be splitting weather. If the weather is sunny or overcast or rainy. So if the weather is sunny, you can see here by splitting with the weather, we can see only two nodes. So there is no S here. So it's a homogeneous set of data. So it is no. So no need of further splitting. So similarly, if it's overcast, we have only one S. We have two nodes and one S. So this is also homogeneous set because we don't have mixture of S and no. So here also we don't need any splitting. But in rainy, we have a set of values which is S and no. Yes and no. So this is non-homogeneous set. So in this node, we're gonna select another feature for separation, which can help us to efficiently separate it into homogeneous features. So this rainy data, which is mixture of yes and no, these are the data which corresponds to that data. So here, if you see, if the data set is big, we need to calculate the Gini for again for the features, and we need to select the feature for splitting where we get the most Gini. But here, if you see, if it's windy, we cannot play in the ground, and if it's not windy, we can play in the ground. Using this, we can build a simple feature. We can do that by calculation. So here, if it's windy, then yes. If it's not, then no. So here we can see in the leaf nodes, we got the homogeneous set. That is, they have only the either the set of yes or set of no. They don't have the mixture. This is the tree structure we would have, um, just because the space is low, it's a bit clumsy. So this is how basically a decision tree works. So first, we're gonna choose this feature for splitting by calculating the more Gini impurity so that we will get maximize the Gini gain. So we will do the process of splitting repeatedly until we get the homogeneous set of data in the other process to the homogeneous set. Let's quickly see the overview of random forest machine learning method. So random forest basically uses multiple decision tree. So just because it uses multiple decision tree, which is multiple individual machine learning models, they are called ensemble methods. So random forest is one of the ensemble methods. So let's see how this random forest works. So before that, why do we need random forest? Why do we need multiple decision trees? So the decision tree has various nodes. So here, let's say we have the maximum depth. So we'll reach to the point where we have more number of nodes and edges, very big tree. So eventually, if we have more number of rules and splitting here at the end, we will have every single data which is present in the data set itself. So eventually in the training data, we can reach any data in the training data by given any prediction data for prediction. So it means that the model doesn't learn anything new, which it in turn means that the model has been overfitted to the training data because we have more depth here and it overfits and it overlearns the training data. So in order to reduce this, we need to use random forest. So here, basically we have three steps: bagging or bootstrap, aggregating, random feature selection, and aggregation. So what is bagging? So bagging is nothing but, let's say we have the data here, the tabular data. We have the rows and columns of data, column C1, C2, C3, and so on, and rows, row 1, row 2, row 3, and so on. So here, bagging is we take only a small subset of the data set here. So here, instead of let's say we have n rows, we take only first 10 rows, or random 5 rows in middle. We take that randomly, so they are not in order. Also, we take that with replacement. So what do I mean by it? So we can repeat the rows. So we can take row 1, row 2, and again row 2 itself. So it's completely random. So this randomness adds more generalization to the model which we do. So for each tree, we take the random subset of data. Not only the data is randomized, but also the feature selection is random. So what do we mean by it? So in the normal decision tree, we take consider all features and take the feature which has the least any impurity, and we split according to it. But here, the subset of the feature which we consider is also random. So here we might consider C2, C3 up to Cn, or we can consider any random subset of features. And in that subset alone for the tree, we're gonna do the splitting. Tagging is choosing the random data with replacement. Random feature is choosing a subset of random subset of features. And the next one is aggregation. So now that we chose the random data and we did the random feature selection, we'll have different trees like tree A or tree B and tree C, D, and so on. So let's say for categorical output, we have let's say two classes, class 1 and class 0. So let's say we have just four uh, decision trees in this random forest. So here tree 1 gave the output 1 for a prediction data, and tree B gave the output 1, tree C also gave the 1, and tree D gave the output 0. So we're gonna calculate the majority of this, so it's called as majority voting. So what's the class which the majority trees give in a random forest? So majority votes. So what we aggregating is just we are basically combining the output of all individual trees prediction in a random forest. So here, this case of classification, uh, we predict the class that gets most vote from all trees. But in case of regression, we don't have the classes. We just predict the average of all tree outputs. So here, this feature, just because we chose a random feature, the correlation is also generalized between the features. So this in turn reduces the overfitting problem in the traditional decision tree.